Okay, so this section is 1.4, shifting, reflecting, and stretching graphs. So a lot of this should be review from Math 2 and Math 3, because we did a lot of these transformations in those classes. But essentially, this is going to be a review of all the parent functions and what they look like, how to use vertical and horizontal shifts and reflections to graph functions, and then how to use non-rigid transformations. This is just another way to say stretches and shrinks. So in general, let's start with the summary. So one of the first days of class that we had together, we reviewed all the parent functions. So you guys should have a sheet that has all of these functions on there. But eventually, essentially what I want you guys to understand is at this point, you guys are expected to know what all of these look like. So if you see a graph that looks like this, you should know it's a linear function. A V-shaped graph is absolute value. A graph that looks like this is the square root function. A U-shaped graph is f of x equals x squared, which is a quadratic function. This is a parabola. A cubic function looks like this. It's kind of S-looking shape. X cubed is the parent function. And then a rational function is f of x is equal to 1 over x, where there is a vertical asymptote right here at x equals 0, and there's a horizontal asymptote right here at y equals 0. So we're going to start this lesson with a review of vertical and horizontal shifts and what they look like. So in all these definitions that you're going to see right here, C just represents any positive number. So if you want to move a graph upwards, you would take the original graph and you would add a number to it. So f of x plus c represents a vertical shift up. F of x minus c represents a vertical shift down. A horizontal shift to the right is where it's f of parentheses. Inside the parentheses, you have x minus a number. So this is to the right. If it's x plus a number on the inside, that means you're actually moving it to the left. So we're going to start with an example. We're going to take the graph of x cubed and we're going to transform it in a few ways. So in part A, we're going to graph g of x is equal to x cubed minus 1. So the easiest way to do this is you want to first recognize what the parent function is. So the parent function is x cubed. So f of x is just going to be x cubed. So if you guys ever forgot or forget what this looks like, you always want to start with 0 and then pick some numbers bigger and some numbers smaller. But we should have sorry about that. We should have this on our paragraph sheet from one of the first days of class. So these numbers are going to be -8, -1, 0, 1, and 8. So if you plot those, 0, 0, 1, 1, 2, 8 is going to be up here. -1, -1, and then this is 10, 9, 8. So sketching that. So this is going to be f of x. So we have to pay attention to is g of x, what they want us to graph. This -1 means that it is going to be a vertical shift 1 unit down. So we're going to take all these points. We're going to move each point from f of x 1 unit down and then sketch the graph of f like that. It's kind of hard to tell because the way that this drops so fast, it looks like they kind of overlap, but just label this as g of x. A good little a good not strategy, but you should always, what I'm trying to say is you should always label your graph. So -8, -8, +8, +8, x-axis, y-axis. So that way, if there's anybody that's reading your graph, they can see what those points actually mean. Okay, so for part B, we're gonna do the same thing, but h of x is x minus 1 quantity cubed. So I'm going to slide this guy up. So h of x is equal to x minus 1 cubed, where again, the parent function is still x cubed. So if we just copy our table from above, 0, 0, 1, 1, 2, comma 8, negative 1, negative 1, negative 2, negative 8. It's going to look something like that. Then this right here, a minus and the inside means that it's going to be a horizontal shift 1 unit to the right. So I'm going to take all of my points. Oops. I'm going to take all my points that I just graphed. I'm going to move them all 1 unit to the right. So boom, 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 and then sketch that. Label your graphs. This is going to be 8, 8, negative 8, negative 8. I'm just choosing 8. You can choose whatever you want. But that way everyone knows that reading your graph that each of those little tick marks is worth 1. Part C, x plus 2 cubed plus 1. What was it? What was it? K. So k of x is equal to x plus 2 cubed plus 1. So again, your parent function is x cubed. So we're going to copy that graph we've done twice already. So 0, 0, 1, 1, 2, comma 8, negative 1, negative 1, negative 2, negative 8. So it should look something like that. So for this function, notice that there's 2 transformations. So let's start on the inside. So like order of operations, you start on the inside the parentheses. So the plus 2 is telling us that this is going to be, number 1, a horizontal shift. Two units left. And then the plus 1 is going to be a vertical shift 1 unit up. So I'm going to take each of my points and I'm going to move them 2 units to the left and also 1 unit up. So this point right here, 2, comma 8, I'm going to take it and go 1, 2, and then 1 up. One, 2, 1 up, 1, 2, 1 up, 1, 2, 1 up, 1, 2, 1 up. So it should look something like that. Label your axes, label your scale. So this is going to be 8, 8, negative 8, negative 8. All right, example 2, we're given some graphs. So it says in parts A and B, the graphs of g of x and h of x are transformations of the graph of x squared. Find an equation for each function. So if you need to do this, it may help you. But let's say that we don't remember what x squared looks like. You can, again, make a table. Start with 0, 1, 2, negative 1, negative 2. If you evaluate these values, you're going to get 4, 1, 0, 1, 4. So 0, 0, 1, 1, 2, comma 4, negative 1, 1, negative 2, comma 4. So it's going to look something like that. So what you're basically doing is you're comparing, if this was x squared what did I do to this to get to this guy? Well, it looks like it only moved upwards. It moved up 1, 2, 3, 4 units. So I have to ask myself, if it's a vertical shift 4 units up, what does that look like algebraically? Well, if this is g of x, because it says it right here, what we want to write is g of x is equal to a vertical shift up means that it's going to be plus 4 at the end of the function. So it's going to be x squared plus 4. For part B, if we already know what this looks like, basically what you can ask yourself is, if this is the vertex right here, this looks like the vertex of this guy. So what did I do for the vertex to travel from 0, 0 to this point? Well, it looks like it moved 1, 2 units to the left and then 1 unit down. So 2 units left and 1 unit down. So algebraically, what we're going to do, h of x is equal to, because they told us it's h of x, a shift 2 units to the left means that on the inside, I'm going to put x plus 2 squared because it's quadratic. And then 1 unit down means I'm going to put a minus 1 on the outside. Reflection of a graph is like a mirror image of the functions. We have 2 different types. We have a reflection in the x-axis, which means that there's a negative in the very front of f of x, and it's going to reflect downwards or upwards across the x-axis. A reflection in the y-axis means it's going to reflect across from left to right across the y-axis. As for this one, the negative is on the inside with the x. So in this example, same idea, but now we're going to ask ourselves, what is the equation when we're talking about reflections? So for part A, it's g of x again. So we're comparing it to the original parent graph of x squared. X squared normally is right here, starts at 0, 0. So to get from here to here, it looks like not only did I move up 2, but now the graph is upside down. So because it's flipped upside down like this, that's a reflection across the x-axis. So reflection across the x-axis. That's also, it's shifted 2 units up. So if I want a reflection across the x-axis, that means that I'm going to throw a negative in front of my f of x, and my f of x was x squared. So my answer to this is going to be g of x is equal to negative x squared and then plus 2. For part B, it also looks like a reflection. Okay, but then what else happens? So if I was normally at 0, 0, but now I'm at 3, 0, I moved 3 units to the right. So I have to ask myself, if I wanted to move 3 units to the right, where do I put that 3? So reflection across the x-axis again. And then it's a horizontal shift. 3 units left. Oh, sorry, 3 units to the right, excuse me. So if I move 3 units to the right, okay, so that means that h of x is going to be negative parentheses, because if it's to the right, I'm going to put a minus 3 on the inside, but I must also put a minus on the outside because of the reflection. So this equation is going to be minus parentheses negative, excuse me, minus parentheses x minus 3 squared. Okay. Compare the graph of each function with the graph of f of x equals the square root of x. So we're going to start with part A. G of x is equal to negative square root of x. Well, this minus right here tells us that this is going to be a reflection across the x-axis. So the parent function here is the square root of x. So from our parent graph sheet, start with 0. Square root of 0 is 0. 1, the square root of 1 is 1. And then we skip to 4 because we know the square root of 4 is 2. So 0, 0, 1, 1, 4, 2. So square root function looks something like this. I'm going to call this f of x. For g of x, okay, reflection across the x-axis. So that means that the easiest way to explain this is you look at the height, how far away this point is from the x-axis. So it looks like it's 1 above. So if I reflect this across, it's going to be the same distance, but now below. So this point right here is now going to be 1 below the x-axis. So right here, I'll plot that point. This point right here is going to be 2 below now the x-axis. So right there, 0, 0, 0, 0 is not going to change because it's already on the x-axis. So it's going to be right there. It's going to look something like that. Scale, this is 8, negative 8, 9, negative 9, x-axis, y-axis. For B, h of x is equal to the square root of negative x. So this minus on the inside means it's going to be a reflection across the y-axis. So take your original function, so x squared, sorry, not x squared, square root of x, 0, 0, 1, 1, 4, 2. Then now, because we know that h of x is going to be a reflection across the y-axis, this is the y-axis. You're going to look at how far away from the y-axis is this point. So it's 1 to the right. So then its new point is going to be 1 to the left. So it's going to look like this. This point right here is 1, 2, 3, 4 units away on the right side. So its new point is going to be 4 units away on the left side. 1, 2, 3, 4. So this graph is going to look like, oops, like that. 9, 9, negative 9, negative 9, x, y. Part C. It's going to be negative square root of x plus 2. So for this one, start on the inside. So if you start on the inside, notice that there's a plus 2. So that means that a positive 2 on the inside tells us that this is going to be a shift 2 units left. So that's going to be the first thing. And then the second thing is going to be the negative on the outside. Tells us it's a reflection across the x-axis. So parent function is still square root of x. So 0, 0, 1, 1, 4, 2. So you're going to take each point, move it 2 units to the left, and then reflect it across the x-axis. So this point right here, since it's sitting already on the x-axis, there's no distance away from the x-axis, so this won't reflect. So this guy's just going to move 1, 2 units to the left, and then you're just going to plot a point. This guy's going to move 2 units to the left, 1, 2. it's one above the x-axis, so then its reflection point is going to be one below, so it's going to be right there. This point right here, 1, 2, it's 2 above currently, so its new point is going to be 2 below, so right there. So this graph looks something like this. Label your axis. This is the y-axis, this is the x-axis. Cool. All right, last thing, stretches and shrinks. So your book refers to anything that is a reflection or shifting left, right, up, and down as a rigid transformation. However, when the graph actually changes shape, it's called a non-rigid transformation. So the different types that we have are vertical stretch and a vertical shrink. The way that you identify that is if there's a number on the outside that's multiplying the entire function. So something like y is equal to 2x squared. This 2 would be a stretch because it is greater than 1. If the value is greater than 1, it's a vertical stretch. If the value is a fraction or decimal that is between 0 and 1, then it's a vertical shrink. When it is a vertical stretch, the graph is going to get narrower and it's going to grow taller, faster. When it's a vertical shrink, it's going to grow wider and it's going to grow at a slower rate. The graph of a function where there is a c value on the inside of a function, so it's something like the absolute value of 2x, like that, or this 2 is on the inside with the absolute value bars. We say it's a horizontal stretch when the c value is between 0 and 1. It's a horizontal shrink when the c value is bigger than 1. So if you guys remember from math 3, this value right here is greater than 1. So the actual a value is you take this number and you do the reciprocal of it. So this would be a horizontal shrink by a factor of the reciprocal of 2 is 1/2. All right. Compare the graph of each function with the graph of f of x is equal to absolute value of x. So for the first one, h of x is equal to 3 times the absolute value of x. So the parent function here is the absolute value. So absolute value of x. So this guy, the numbers we chose stay the same as most of the other graphs that we picked or we practiced last week. So throwing this in and just copying off of our parent sheet, you get 2, 1, 0, 1, and 2. So the parent graph looks something like this. So absolute value is a V-shaped graph like this. We're gonna call this f of x. Now, this is a vertical stretch by a factor of 3 because the 3 is on the outside of the function. So all that means is for each x value, you're going to take its height and multiply it by 3. So this right here is a point 1, 1. Instead of 1, 1, I'm going to take the 1 and triple it. So this is going to be 1, 3 for the new value. This height right here is 2. So tripling it, you're going to get 6. So 2, 3, 4, 5, 6. 2, 6. This right here, the height's 0. So if I triple it, 0 times anything is itself. So you're going to get 0 still. So this graph is going to look like this. And this is h of x. And if you remember from up here, we said that a vertical stretch is going to make it narrower and go taller and faster. So if you can see, the red points are all taller than the blue points, and the graph itself became more narrow compared to the parent function. So if we label our scale, we got 9, 9, -9, -9, x, y. For B, we have g of x is equal to 1/3 times the absolute value of x. So for this function, okay, I'm going to be multiplying all my values by 1/3, but the only one that's going to actually be nice for us is going to be 0, because 0 times a third is just 0, but these numbers are going to be fractions. So I'm actually going to be kind of clever here. For my parent function, I'm going to pick 0, 0. For the other values, I'm going to pick 3 and 6 and -3 and -6, because when I plug those into just absolute value, I'm going to get, so this is for f of x. So if I plug this into absolute value, I'm going to get 6, 3, 3, and 6. So my parent graph, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 1, 2, 3, 4, 5, 6. So the parent graph is going to look something like this. For g of x now, because this is a third on the outside, that tells us it's a vertical shrink by a factor of 1/3. So in other words, I'm going to take each of these heights of f of x, and I'm going to divide them by 3. So this is why I chose 3 and 6, because then these answers are going to be much nicer to deal with than graphing 1/3 and graphing 2/3. So for the new graph, instead of 3, 1, 3 divided by 3 is 1. So the new point is going to be 3, 1. Instead of 6, 6, 6 divided by 3 is 2. So 6, 2 is the new point for the new graph. 0, 0 stays the same. -3, 1, and then -6, 1, 2, 3, 2 is the other point. So this graph looks like this. And this is g of x. And then this is 9, 9, -9, -9, x, y. Okay, last example. Compare the graph of h of x is equal to f of 1/2 x with the graph of f of x is equal to -x cubed plus 2. So we have to do a couple things here. So the parent graph of this guy is going to be x cubed. So I'm going to say that g of x is just x cubed, because if I know what x cubed looks like, then I'm able to, this is going to reflect it, and this is going to move it up 2 units. So x cubed we got -8, -1, 0, 1, and 8. So it's going to look like something like that. So this is going to be g of x. So for each of these points, order of operations, I'd actually do the reflection here first. So I'm going to reflect it across the x-axis, and then I'm going to move it up 2 units. Well, this is already on the x-axis, so I'm going to move it up 2 units, 1, 2. Reflect it across the x-axis. and then move it up 2. 1, 2. So that point actually stayed the same. Reflected across the x-axis. So this is at +8. So the new point is going to be way at -8 and then up 2. 1, 2. Reflected across. So this is 1 below, so it's going to be 1 above and then up 2. 1, 2. This is 8 below right now, so the new point is going to be 8 above, then up 2. 1, 2. So that graph's going to look something like that. So this is f of x. So h of x, what they want us to graph now is f of 1/2 x. So this 1/2 tells us that it is a horizontal stretch, because if it's less than 1 but bigger than 0, it's a stretch by a factor of the reciprocal of 1/2, which is 2. So all we're going to do is we're going to take each point and we're going to stretch it 2 times away from the y-axis that it is right now. So in other words, if we look at this point on f of x, it's right now 2 units away from the y-axis. So if I want to stretch it away, because it's a stretch, I want it to be the distance to grow. So right now the distance is 2 away, so the stretch is going to make it 4 away. So 1, 2. I'm sorry, 4. 2 times 2 is 4. So 1, 2, 3, 4. So the new point's going to be right there. This point is 1 away right now. So if I stretch it away from the y-axis, it's going to be 2 away. So it's going to be right there. This point's sitting on the y-axis, so it's not going to change. This point is 1 away from the y-axis. So if I stretch it times 2, it's going to be 2 away. So it's going to be right there. And then same thing, this point is 2 away right now. So if I stretch it by a factor of 2, it's going to be 4 away. So 1, 2, 3, 4. So I'm going to draw a point right there. So it's going to look like something like that. I'm going to highlight it so you guys can see. Okay. So then last step is to label your scale. So 9, -9. Call this one 8. This one -8. X-axis, y-axis. And we are done.